All right, let's dive right in. Today, we're taking a journey to the very foundations of reality itself, into a world where all the rules we think we know just completely fall apart. We're talking about quantum physics, the absolutely bizarre, mind-bending set of rules for the ultra-small. In our everyday world, things just make sense, right? If you throw a baseball, it follows a nice, predictable path. Your coffee cup stays on the table unless you move it. That's classical physics. But if you could shrink down to the size of a single atom, everything, and I mean everything, changes. There are no more definite paths, just fuzzy clouds of probability. Objects aren't just solid things. They're somehow both a particle and a wave at the exact same time. And this leads us to the really big, unsettling question at the heart of it all. What if the universe, at its most fundamental level, isn't some perfectly predictable machine? What if it's all just one giant cosmic game of dice? That's the mystery we are going to unpack right now. So, to really get how this revolution happened, we've got to rewind the clock to the late 1800s. Physicists back then were feeling pretty pleased with themselves. They seriously thought they had pretty much the whole universe figured out. But there were a couple of nagging little problems, weird experimental results that just wouldn't go away, especially when they looked at light and heat. Okay, so one of these big headaches was something called black body radiation. Now, that sounds super complicated, but it's not. It's really just about the glow any object gives off when it gets hot. Just think of a poker in a blacksmith's fire. It starts to glow red, then it gets hotter and turns orange, then white hot, right? Well, physicists wanted a formula, a rule that could predict exactly what colors, what frequencies of light it would spit out at any given temperature. Now, here's where it got weird. All the best theories they had, everything they knew about waves and energy, made a prediction that was completely bonkers. Their math said that as the frequency of the light got higher and higher, moving up past visible light into the ultraviolet range, the amount of energy it was radiating should just shoot up towards infinity. I mean, this wasn't just a little bit wrong, it was physically impossible. It would mean that any warm object, even your cup of coffee, should be blasting out infinite amounts of deadly high-energy radiation. And, well, it obviously doesn't. This spectacular failure of the old physics got a suitably dramatic name, the ultraviolet catastrophe. Theory had just slammed into a brick wall. So, who finally figured out how to break through this wall? The answer came from a physicist named Max Planck. And honestly, he wasn't trying to start a revolution at all. He was just trying to make the math work. And he came up with what he later called an act of desperation, a wild guess that would accidentally change science forever. So Planck threw this crazy idea out there. He suggested that maybe the tiny little vibrating parts inside the hot object, he called them oscillators, couldn't just have any old amount of energy. He imagined that their energy could only exist in specific, discrete packets. He called these packets quanta. And that is the core idea of quantization. Think of energy not as a smooth, continuous ramp you can stand anywhere on, but as a staircase. You can be on step 1, or step 2, or step 3, but you can never, ever be floating in between the steps. And just by making that one assumption, that energy comes in these little chunks, Planck's new formula suddenly described the experimental results perfectly. The ultraviolet catastrophe was solved. The quantum age had just begun. But Planck's idea? That was just the starting gun. Because in 1905, a young, unknown patent clerk named Albert Einstein took this quantum idea and ran with it to solve another huge mystery that was bugging physicists. This puzzle was called the photoelectric effect. Here's how it went. You shine a light on a piece of metal, and poof, electrons get knocked loose. But the way it happened made zero sense. For one, the electrons were ejected instantly, even if the light was super dim. And making the light brighter didn't make the electrons fly off any faster. It just knocked out more of them. The only way to make the electrons faster was to change the light's color to a higher frequency, like going from red light to blue light. The classical wave theory of light had no explanation for any of this. Einstein's solution was, well, it was breathtakingly simple and totally brilliant. He said, what if Planck was right, and light itself is actually made of these little energy packets? He called them photons. Each photon acts like a tiny bullet of light, and the energy of that bullet is determined only by its color, its frequency. And this explains everything perfectly. One photon bullet hits one electron. If the bullet has enough energy, it knocks the electron out instantly. Brighter light just means you're firing more bullets, so you knock out more electrons. And higher frequency light, like blue light, means you're using higher energy bullets, which is why the electrons fly out faster. Genius. Okay, so let's get this straight. Light, which everyone was sure was a wave, can also act like a particle. This raised a really fascinating question for a young French physicist named Louis de Broglie. He decided to take this whole idea and just flip it completely on its head. He was thinking, okay, let's just follow the logic here. The universe likes symmetry, so if waves, like light, can pretend to be particles, then why not the other way around? Shouldn't particles, like electrons, also have some kind of wave-like nature to them? It was such a wild idea that he actually proposed it in his PhD thesis, suggesting that all matter has a wave associated with it. And the proof for this absolutely wild idea, it comes from probably the most famous, most mind-blowing experiment in all of physics, the dual-slit experiment. So if you fire electrons, one by one, through two little slits like tiny paintballs, you'd expect to see just two stripes on the screen behind them, right? But that is not what happens. What you actually see is an interference pattern, a whole series of stripes, which is the exact pattern you get when waves pass through two slits and interfere with each other. This revealed something just incredible. It means that a single electron, when you're not looking, somehow goes through both slits at the same time, like a wave, and interferes with itself. It was the ultimate validation of de Broglie's matter waves, and it cemented this central, bizarre truth of the quantum world. Everything is both a particle and a wave. So this whole particles are also waves thing, it leads us to the final and maybe the most profound piece of the quantum puzzle. Because if a particle is also a wave that's all spread out, how can you ever know exactly where it is? This is the question that led Werner Heisenberg to a startling conclusion about the fundamental limits of what we can even know about the universe. Now, you know who hated this idea? Albert Einstein. He absolutely could not stand it. This new physics was suggesting that the universe, at its very core, was built on pure chance and probability, not on predictable certainty. He famously protested, saying, "God does not play dice." Yeah, well, as experiment after experiment would prove, despite Einstein's deep objections, the quantum world absolutely does play dice. And this is all wrapped up in what we call the Heisenberg uncertainty principle. Now, this is crucial. This isn't about our tools not being good enough. This is a fundamental property of nature itself. There is an inherent trade-off built into the fabric of reality. The more you pin down a particle's exact location, the less you can possibly know about its momentum, and the other way around. You can never, ever know both perfectly. Okay, so let's just take a breath and recap what this new reality looks like. We found out that the universe comes in tiny, discrete packets, or quanta. We've learned that everything, from light to you and me, has a bizarre dual nature, acting as both a particle and a wave. And finally, we've realized that at its very heart, the universe is governed by probability, not by clockwork certainty. And as weird as all this sounds, this is the understanding that makes almost all modern tech, your phone, computers, lasers, possible. And that brings us to the final, really deep thought. You see, the quantum revolution didn't just upend physics, it completely changed philosophy. It forces us to ask these massive questions about what existence even is. If an electron doesn't even have a definite position until we go and measure it, if the very foundation of the universe is just pure chance, what does it even mean for anything to be real? That's a question that physicists and philosophers are still wrestling with to this very day.